Yeah, so this is really a talk which is based on the course I'm giving at CATS on machine learning. So I wish to thank various directors, and in particular Adrian, for allowing me to give this course on machine learning at CATS. So it's based on this. And so I would like to mention some collaborations and papers. I have two undergraduate students, Erin Babbitt and Shelby Grossman, who are finishing a paper on the new history of a neuron and all these kind of things. And I would like to mention the following research papers with Kamal and Michaela, and also with a group in Italy and Kamal on, the first one is really neural networks in the bicomplex case, and the other one our papers are kind of related to machine learning and mathematics, but it is really to hint that when you do machine learning, there are a lot of mathematics which intervene. And finally, I don't know if he's online, but I'd like to thank also Palle Jorgensen, who we discussed a lot on robot-synchronous spaces and machine learning. So in any event, the main point of the lecture would be, so I would like to discuss the history of the structure of a neuron, the so-called neuron doctrine. Then I would like to discuss the history of origin of the perceptron and artificial neural networks, the perceptron controversy, and more generally, machine learning. I would like to study the connections between them and also the mathematical tools which are used for the perceptron, and I'll discuss also other mathematical tools which are used in machine learning and or in artificial neural networks. I mean, artificial neural networks is only part of machine learning, of course, and we'll see a lot of other tools like positive definite kernels, like dynamical systems and hypercomplex analysis. And not so hidden agenda in this last point is to show that I think this kind of course would be of interest for students at the MPP program. So what is the talk about? So I would like to describe a path really from the discovery of a neuron, the fact that the neuron was an independent unit. I mean, it took some time to discover, as I saw the neuron doctrine, to a theory of artificial neural networks. And around the 60s of the previous century, there was the perceptron, which was discovered, which is really the building unit of artificial neural networks, if you want. And in some sense, a certain neuron model inspired the perceptron, and the latter is a building block of artificial neural networks. If you allow me to backtrack, you see that here it's in red, the neuron doctrine and perceptron controversy. It is in red because the path was far from being smooth. There were a lot of opposition and a lot of problems in this. So it was far from a smooth path in both cases. So we talked not about the brain, that would be neuroscience, but about the field of neural computation in some sense. That's more about this. I would like just to define what is, to the beginning, what is neural computing. I'll just take a definition from this book. Technological discipline concerned with information processing system that autonomously develop operational capabilities. This is important, autonomously develop operational capabilities in adaptive response to an information environment. This is a fancy definition. I mean, in plain words, it's been just to mimic the brain, if you want. But this is a more fancy word to say it. And some references, not really related to the talk, but to the neural computing in general. Very interesting references. So the last one is on model brain function and the world of attractor neural networks of Daniel Amit is of special interest because it really shows how dynamical systems appear here. The last one has a strange title in some sense, simulated annealing and Boltzmann machines, and I will discuss what it is in the next slide. And then we'll go to the topic more on the topic of the lecture. So, what is annealing? So in material science, I mean, when you have a material, quenching is to make the material very hard, and annealing is a procedure to have it more smooth and to lower the energy. And what is the relation with what we are doing here with the models? Well, there is this paper, a very old paper of Metropolis, Rosenblatt, and Teller. Teller here is a Teller of the hydrogen bomb, and they made they introduced some random method just to get a lower energy, to get the lower energy. And the idea is that memory, this is towards the end of the lecture, I would like to say, at least in the artificial neural networks, memory can be seen as a energy minimal states in dynamical systems. So this is, if you want, the connection with Metropolis and Tele. What was before, so let me a little bit backtrack once more, that was really some references on neuro computing, but I would like to proceed. And so I mentioned the perceptron. So the perceptron will play an important role in this lecture. So what is a perceptron? What is interesting that most of the people in this field, they are not mathematicians. I mean, Rosenblatt, as you see, he died very young, but he was a psychologist, and he defined a perceptron, any theoretical system which attempts to explain the psychological function of the brain. Once more, a brain model, if you want, he writes this in a more fancy way, and we'll see precisely what it means. And as I already said, it is really the unit of, the building block of artificial neural networks. But that was before that, of course. It was around 62. This is his book. As you can see, the title is Principle of Neurodynamics. It's from 60, so it's very far, really, from machine learning, one would think. So, what is a perceptron? So, as we will see in the sequel, it is really an algorithm. So let's say you have two classes of elements, and you can separate them by an hyperplane. So there are two pictures here, it is given ahead of time, but that you can, the hyperplane will not be unique. In the second picture here, forget about the fat strip. I mean, the fat strip would be connected to support vector machines. This is not the topic. Just look at the two lines. So you see that the hyperplane will not be unique in general. I mean, of course, you can look at cases where it will be unique, but in general, it will not be unique. And the perceptron algorithm, which you will see in the sequel, allows to find an hyperplane in a bounded number of times, iteration. The point is bounded. It will be always finite. I mean, if you start with finite classes, whatever you do, it will always be finite. Take one, I mean, it will be always finite. But here, with some hypothesis, you can get an upper bound on the number of iterations you will need. So this is very important. Of course, it will depend on your original hypothesis. But when I say bounded, I want to distinguish it with finite. With some hypothesis, we know that it will be less than a certain number. It will be clearer when I give a...
Sorry, the object in question has a numerable, or it can be on any cardinality?
The classes, in fact, when I wrote, let me say, no, I think it can be any cardinality. I would have to double check.
Okay, so it's not, it can be a situation in which there is only one plane.
No, because you have an hypothesis that they need more than one plane.
And we need more.
Yeah. No, I mean, it's not a unique situation. You will see. Because if it's a unique, it will not work.
Okay.
But there is a condition, something like that. You suppose that there exists a vector A. You don't know what is this vector, but you suppose it exists. So you have the supremum, or I think the infimum of the inner product of the A with all elements in your classes is strictly positive. And here is this delta. The bounding will be in terms of this delta. Basically, it will be 1 over delta squared. So even if here there is an infinite number, it will be bounded by, I think, 1 over delta square or something like this. So which is very powerful. And you know that it will stop. Of course, in principle, you don't know because you don't know delta. But even if you run it, you know that it will stop in principle. So you can hope that in practice, it will also stop. And the second picture, just want to show that you don't have uniqueness. Now, in the picture, I don't see it. Yeah, you see a large strip. This is when you want to have support vector machines and have to separate them as wide as possible. But this is not the topic. Simply, I just pick up this picture and there was a two together. Okay.
Daniel, sorry, existence is not guaranteed either.
No, it is. Once you suppose that there is this A, there is an algorithm which will compute one.
So they're independent of what class A, class
Your
C.
starting point is the following. You have two classes.
Right.
You know that you can separate them.
Oh, okay, I got it.
You know, because otherwise...
Okay, got it, okay, yeah.
So it's a lot of hypotheses,
Yeah.
but the fascinating thing is that then with hypothesis on your data, you can get an upper bound of the number of iterations.
Then you always can get an hyperplane, not the
No, an upper plane.
hyperplane.
Yes. Then when this cannot, we will see how to go to higher dimension, but this is towards the end of the lecture. Okay? So, as I said, it's always finite if the classes are finite, but we get an upper bound. This is important. Okay, so I mentioned the neuron. So, what is a neuron? I will mention. So here we have a scheme of a neuron. So you see there is the cell body, and then you see a very large appendix, which is called the axon, and smaller ones, which are called the dendrites. And what happens in the brain is that, okay, they're not connected. This is the whole point. But let's say that in approximation, they're kind of connected. The information goes in one direction, and one axon is not connected, but close to the dendrite of another one. And when the information is processed, when there is an action potential, they connect together, and otherwise they separate. And it goes only in one way. So this is, for the sequel, it's very important, this picture. You have a long appendix, which is called the axon, and it's in one-way direction. So the information, which is in terms of electrical or chemical signal, will go along the axon, from one axon to the dendrite, and so on. It doesn't go back, there is no feedback. And once more, they're not connected together, but almost connected. And when information passes, they just stick together. So this is, there is much more, of course, there is much more in the neuron, but this is we'll see back this picture in the sequel, but and the connection, so it's called the synapses and the synaptic gap and the synaptic connection. So what can I tell more? There is much more to say, but here this is what I want to say. And of course, what I said is wrong. For us, what we need is correct. I mean, this is correct. But there are a lot of kinds of neurons, not only these ones, one should say, and this is an oversimplified figure, but for the purpose of this lecture, this is what we need. And in new aspects of neuron doctrine, sometimes you have counterexamples, like in mathematics. Yes, you have sometimes dendrites can have synaptic outputs, and axons can have inputs from other axons. So they can be counterexamples. But the picture I wrote before, I showed before, is very important and is relevant. It's not that suddenly doesn't exist. And of course, gray matter, what matter? The gray matter is really the neural cell bodies, the axon terminals. And the axons are coated with myelin to protect them. This is really the white matter. Yes, so this is so this picture will be very important. One long appendix, if you want, and a lot of little ones, and there is in the middle the nucleus to process information. And when it goes from one neuron to the other, it's called an action potential. Yes, so this is at least this is what I could gather. Okay, so this story for the purpose of this talk. So the history of the discovery of a neuron, I think, is very important, and the neuron doctrine, to understand how the artificial neural networks really evolved. So I would like to say some steps. It's not it's kind of an history, but there are only the main steps. It's not a history of a neuron from A to Z. I mean, just some main steps. First of all, at the beginning of the 19th century, microscopes got better. Before that, there was no way to see what is inside the brain. When microscopes, and Michaela pointed me that there is a misprint at microscopes, so I saw it. But when the microscopes got better, then you needed new histological methods. And then come into place a very interesting character, Camillo Golgi, who developed histological methods, new histological methods to be able to see better what would be with new microscopes, even more powerful microscopes.
Sorry, can I make an Italian? Camillo Golgi.
Okay.
Camillo Golgi.
Golgi. So,
with the handles. Yeah. Right?
Yes.
Otherwise, you're not Italian.
Yes.
Exactly.
No, that can be worse because
I think that is the first Nobel, Italian Nobel Prize.
Yes, he developed new methods based on silver staining. But I think silver staining, I mean, before computers and the cameras we have, and when we have usual cameras, I think it was one of the ways to develop pictures. Anyway, the silver staining allows to visualize elements. And he got a Nobel Prize in Physiology or Medicine with Santiago Ramon y Cajal in 1906. What is interesting is that he developed the methods which allowed to see that the axon and the dendrites are not connected together, but he refused to the very end to accept this theory. And even in his speech, in his Nobel Prize speech, he mentioned the following. This is from his speech. However, opposed it may seem to the popular tendency to individualize the elements, I cannot abandon the idea of a unitary action of a nervous system. But they're not connected, it's an individual unit. But it has been found thanks to the methods he developed. Now in life, one has to be patient because he developed this when he was 28, but he got the Nobel Prize 35 years later. So that's also interesting. So various two questions I mentioned related to do the nerve fibers form a continuous network and so on, but this is not, I want to let me proceed. So this is a Golgi plate. Okay, so of course from here you cannot see that the neurons are separated, but I assume when you look at the microscope with this, then you can kind of see that they are separated, the neurons. Okay, so some more steps. So still, here microscope doesn't have a misprint. So Theodor Schwann was one of the first to suggest that the brain was made of individual cells. He's a proponent of cell theory. Both plants and animals are composed of cells, but this was not accepted for the brain because you cannot really see in the brain. I mean, you needed the methods of Golgi and maybe, but even then you cannot really see, so it was not really accepted. I mentioned, and this is not a list of all the persons, it should be clear. I mean, I just mentioned some high points. William His, transmission without continuity is possible. And then a very interesting character. In this talk, I mentioned a lot of Nobel Prizes in physiology or medicine, but Friedhoff, he got the Nobel Prize, the Peace Nobel Prize. He was kind of a polymath. So his thesis was also on the fact that there is no connection between the axon and the dendrites. But then he left, I guess, biology, and he was in politics, and he got a Nobel Prize in 22, the Peace Nobel Prize, because for his action for the refugees, and in particular the nonsense passports, which were documents given to the refugees in 1938. And he was also an Arctic explorer. And you see here the prize motivation was for his leading role in the repatriation of prisoners of war in international relief work at the League of Nations High Commissioner of Refugees. So I assume he could have gotten also the Nobel Prize in medicine, but he got a prize. So this is a Groenland, which he crossed. I think he was the first three to cross it. So you see on the right, this is Europe, and on the left you can see Canada. So it's an island. I mean, it's not only ice. I mean, it's really an island. And here you can see a nonsense passport in French, because then I think French was the language of diplomacy. So
do they still exist?
No, in 1938 they stopped. At least it's what I read. Okay, so one more remark, that the term neuron was coined by Waldmeyer in 1991, and there are a lot of names. Here I mentioned Waldmeyer, Monica Jal, and Sherrington about understanding that these are not connected together. And here I mentioned once more Santiago Ramon y Cajal, who he got a Nobel Prize for this, really. So it's built on all the other people, of course, but he was, I guess, the main proponent, and also Sherrington. And as I said, it's called the synapse, the connection between the axon and the dendrite. Okay, so this is Santiago Ramon y Cajal, and this is a great book. I mean, there was a book 25 years before, but this is a re-edition, Foundations of a Neuron Doctrine, where there is a whole history and a really great book. Okay, so apart from, so what is a neuron specificity? It's a cell, but it does something more than other cells. I mean, it processes information. So a neuron processes information. How is information processed? So you will need mathematical models for a neuron to see how the information is processed. And I would like to mention what's called the Hebbian rule, which basically says neurons who fire together grow together, basically. This is what it says in other words here. I mean, I will not read the sentence, but basically it says if two neurons are together, are close together and one grows, I mean, they will grow together. So that's basically the idea. And if you want in more other words, learning is doing adjustment. Now, but there are really two parallel questions, if you want, a mapping of the brain and models for neurons. So for the mapping of the brain, there is an interesting character, which is the aplysia we mentioned. So Eric Kendall, who also got this Nobel Prize, thought that, well, our brain has so many neurons to make a model, but you can take a simpler element, simpler animal. And the aplysia has 20, he's not the only one who did such things, but 20,000 neurons. And then you can map, basically. When the neurons are big, this is Kendall, but this is the aplysia. The neurons are big. And so you can map which every neuron is doing, basically, or at least you can try to map. So this is about the mapping of the brain.
It has a few number of neurons, but bigger.
And bigger, yes. Yes.
And he's intelligent?
I don't think so. But on YouTube, you can see Eric Kendall is a very, very nice character, and he's giving a lecture, I think, at MIT or Stanford. He has his aplysia here in a bocal, and he asks the students to touch them. He shows them to students. Very, very, very nice person. Okay, in any event, that's also mapping of a brain. But let's say about the models. So in the mathematical models, you can think of two kinds of models at least. I mean, one would be based on physiology. So really, this is not the models which are interest for us, but I will mention them. And then models maybe on a higher level, like more mechanical. So for biological models, there is of course a huge literature. I would like to mention a paper from 2007, Louis Lapic, Recherche quantitative sur l'excitation électrique des nerfs traités comme une polarisation. And this model is still valid. What is interesting that he wrote papers with his wife, and in the paper it was explicitly written that it was joint work with equal collaboration. So Nicolas Rachevsky, which was a mathematical biologist in Chicago, and I mentioned him because Pitts, who is an important character in the talk, will be mentioned in the sequel, and Eugene Huxley, who Nobel Prize for their model in terms of ordinary differential equations. So when I teach ODEs, I tell my students, you can get a Nobel Prize if you get the correct ODE, but it doesn't give them motivation, unfortunately. But they are it's also easy. There are bifurcation, catastrophe. I mean, it's a bit difficult. And another more recent Nobel Prize in 14. I just mentioned this just to, there is a lot of activity, research activity, and these are just 4 of them that have to be. But then we get to the part which is more of interest in this lecture. So up to now, if you want to do some generalities, and I would like to get to now we're getting closer to the perceptron. So we want to models on a higher level, more abstract oriented. And this is McCullogh, Pitts, Rosenblatt, and Hopfield, basically. Now, if you think about it, as I said before, a neuron is a 1-0 system. I mean, of course, in practice, maybe it is not, but this model we have, it's a 1-0 system. Or it fires or it doesn't fire. So you can view it basically like in one-to-one correspondence with logic, really, because with 0-1, with Boolean functions. So this is what McCullogh and Pitts, they try to do. So let me mention some words on McCullogh and Pitts. There are two completely different persons, and then the model they made. So McCullogh, he had philosophy, psychiatry, and neurophysiology. Sorry, and he was a neuropsychiatrist, and he was looking for what he called a psychon, like an elementary unit of a thought, of a least psychic act. I mean, I don't think he did very much on it, but that was his dream. And that would be the atom to chemistry then. And Pitts was totally the opposite. He was a runaway guy. He was a mathematician. The story says that he met by chance Russell in a park, that he was in the library and read all the book of Russell and Whitehead during 3 days. A lot of stories, maybe they are true, maybe they are not true. The point is that he was interested in logic, and that with the interest of McCullogh, it just fit together. This is the important which we can take from these. And they began to work in 42 in Chicago, when McCullogh was at the Illinois Neuropsychiatric Institute, and Pitts was in Rashevsky group at University of Chicago, which I mentioned before. So about this history of this collaboration, there are interesting paper from Tara Abraham. I will not read them, but these are two papers which these papers, they do not mention, they are not related to the connection of Pitts with Norbert Wiener. I mean, for the analyst in the group, our Wiener, yes, but toward the end of his life, Wiener was interested in such topics. He took Pitts with as a PhD student, and then from one day to the other, was over. And then, this is a Wiener, if you want. And so the main idea in the model of Pitts, of McCullogh and Pitts, and in 2 slides, that will be really the key of the lecture, if you want, the main key of the lecture. The main idea is that in logic, in propositional logic, if you want, there is true and false, and the neuron off and on. And so you can make a connection, and hopefully you can model everything. So they made a number of assumptions in their paper to have a model, which are based on the model for the physiological model of a neuron. It's all one process. You need a number of synapses. You need a certain number of input for an output to be given to fire. And these are the very important hypotheses. The other 3 are also important, so I will not read them. The first one says that it's 0-1, and the other one, if you want, you need enough input so for the neuron to fire. And of course, these assumptions were directly inspired by neuron biological structure.
What does it mean? One is 0-1, and the other you need enough impulse to fire.
It means that, look back, let me, sorry, where was it? Yeah, you see, here you have your neuron. So you need to have enough inputs to the dendrites so that it will be charged enough, if you want, so that it will fire. This is what is meant.
Okay, but then the state
would be 1.
1 or 0.
Yes.
There is no intermediate.
No, there is no intermediate.
In any case.
No, in any case, it should not be intermediate. Yes, this is ready. Maybe it was not written to be there, but it is or 0 or 1. Absolutely. And so here you see the McCullogh model, and of course, from far away in the fog, if you want, it is the same. You have inputs, but here these inputs are 0-1. Soon they will not be 0-1 anymore. And you have a function g. I have to write what it is. It is a nonlinearity. Without the nonlinearity, one cannot do anything. And then the output will be 0 and 1. But this is a model, and you can see better here. But before, allow me to backtrack once more. It's directly inspired. So that's why this model of a neuron was important. And you see, you have inputs and you have weights. They are not written here. The weights do not appear on this little little intervals which model the dendrites, but each one has a weight. And so the input is the sum of a wj xj, let's say at time t. B is just a bias if we need a bias. If this is positive, it fires. F is a heaviside function, otherwise it is 0. So this is a way to model this is a McCullogh Pitts model. And so let me just repeat, the WJ, the weights of the input are the counterparts of the dendrites in some sense. They are not, in the model of Rosenblatt, they will be updated. Here, they are not updated. Rosenblatt is basically the same thing. Simply, the weight will be updated and the inputs will not be 0, 1. But the output will always be 0, and 1. And the biological action potential is modeled by the heaviside function. You could think of other functions. I mean, the heaviside function is this one. You could also think later, not for this example, but you could think of functions like, which would be, I mean, one can think of other functions in practice, but for this model, we need really 0, 1. So the heaviside function is the base. And the nonlinearity is the key here. I mean, without the nonlinearity, nothing would be possible.
B is also is determined by the neuron. It's a value that depends only on the neuron.
I guess yes. It is fixed. It's a bias. They call it a bias. But usually we put 0 in fact.
Right.
If they're models, they are like a minimal level.
Minimal level to work.
Yeah. It gives some more freedom.
And I guess different neurons are going to have different Fs.
Yes. No. The F is the same for everyone.
It's the same for every neuron.
The number of inputs and the weights will be different.
I see.
So the number of impulses is X. X is the number of impulses and V is the
weight, yes.
Yeah.
But let me backtrack here. The number of inputs will be different from each one.
The number of inputs, the weights of the inputs.
Yes, but only one output.
Only one
and
output.
The one output is fixed by a heaviside function, so it will be 1 or 0.
Okay.
And so they, so this is from their paper. They have some logical pictures. I mean, it's a bit difficult to read. And so let's have model. Before I go to Rosenblatt and the perceptron, I would like to mention a forgotten character and to make some shameless self-promotion. So there is Claude Shannon. Claude Shannon he created information theory and the entropy. I mean, entropy was also by von Neumann and other people, but in an independent way, he developed entropy. But what he also did for his master thesis was that he connected all the logical functions in terms of and off with mechanical systems. So he was very close to this kind of ideas. And but he did other things after that. I mean, information theory was in 48. And at CAT, there is this course, information theory from classical to quantum, which sometimes is given. I mean, when overload is allowed. So this is the perceptron of Rosenblatt. So it's the same picture as I said before. It seems the same picture. The only difference is that the inputs may be any number. The inputs need not be 0, 1, and but this otherwise it is the same idea. And of course, Rosenblatt he quotes McCullogh Pitts. This is just a stage. But Rosenblatt went one step further. He used this as a classifier, as I will explain later, to be able to classify two classes which can be separated. I mean, that was not done by McCullogh Pitts. They did a lot of things. If you can understand the paper, but they didn't do a classification. This is not the point they had in mind. Rosenblatt was a psychologist. He wanted to do things which are related more to the brain and classifications and different kind of problems. So in any event, so can we, so to go back to, now we have a perceptron, or even with a McCullogh Pitts model, can we realize or generate or simulate any Boolean function of any number of variables? So let's just see. Let's say you want, maybe, I'm not in logic, so maybe I didn't take the official notation. For me, X and Y are two Boolean logic, and X union Y is the union. I mean, like maybe there is another term, but it would be phi of X plus Y minus 1. Why? Because you want at least X or Y to be 1, then this would be at least 0, and so it would be 1. But if the two are 0, 5 minus 1 is 0. The intersection is the same. I mean, and if you have a number of any number of Boolean functions, it will be the same. I mean, for the union and the intersection. Now, can we realize any Boolean function in terms of a finite number of variables with one perceptron? One perceptron, I mean, the answer is no, and this led to a lot of problems. But you see,
I don't understand. Is x and y at 0?
and then you get minus 1.
F or minus 1?
If x and y are 0,
Yeah.
then x plus y minus 1 is minus 1,
Yeah.
and phi of minus 1 is 0.
Ah, okay.
And let's if x and y are 1 for the intersection, then 2 minus 2 is 0, and phi of 0 is 1. Because I took the beside function to have the one here.
Okay.
If I took the one here, one would have to change a bit.
Mhm.
But you see, now think about the following. Suppose that I have at this point 0, 0, 1, 1, 0, 1, and 1, 0. It corresponds to a certain logical Boolean function. I will mention this, but this you cannot separate by a straight line. This. So that was the Perceptron controversy. You see, you look at the XOR function, or if you want the symmetric difference in sets. So
Aditi has a question. Could you read the question, please?
Yes. Do the domains of the two outputs on off of the Heaviside function represent the two classes of the perceptron algorithm?
No, I'm not sure. I think I will give a better answer when I present perceptron algorithm. Right now, I cannot really answer the question as it is. The phi will allow you to change at each step the hyperplane, the model for the hyperplane. But here we don't see it yet. We are not yet at the hyperplane. But little patience, when I get to the algorithm, you get to. So you see, the XOR is this, and there is no way to separate by a straight line. And this led to the so-called perceptron controversy, because people said it was useless because of that. And in fact, that's not true, because even when you look, and they said that, we weren't even reading the book of Rosenblatt. When you read the book of Rosenblatt, he mentions that you cannot with one, but you can with a lot of layers. You can realize any Boolean function. But one thing was missing in the 60s, and what was missing was the feedback, what's called the back propagation. And without that, it was because of that, and not because of the perceptron controversy. But there was a lot of bad blood there. In any event, you can express XOR with 3 or even 2 perceptrons. Here are the picture. So you see, let us look at the first one with the 3 perceptrons. Each phi is a perceptron, really. So let's say that x and y are 1. So I have phi of 1, which is 1, and I have phi of minus 1, which is 0, and 1 minus 2 is minus 1, so the phi is 0. Suppose that x is 1 and y is 0, so you have phi of 0, which is 1, phi of, once more here, 0, which is 1, and 2 minus 2 is 0, phi of 0 is 1. And the other one is a bit more involved, but these are the way. My two next slides are they are redrawing, which I drew very. First of all, it's a misprint, and the drawing are very not so nice, but I decided to keep them. But the idea is that with any number of sorry, what I wanted to say, it already hints at new kind of problems in mathematics, because you see the functions you get are sum of composition of sum, and in classical analysis, classical problem, we don't see such functions. But here you have one given function maybe, and then you iterate it, you add them together, but with one given function. And these are kind of problems which are not from classical mathematics, I would say. Okay, so here are the two pictures. Here it should be a +1 in the red. Here it's a misprint I had. It should be a +1. and this is our picture. So the pictures are not nice, I apologize, but really these pictures, if I backtrack, are just to rewrite these in a picture way. Okay. So the perceptron, I can be more than 1 hour, yes? How much do I do?
That's
Yeah, we have to
because the
slot
point
it
of
to
the physicist speaks 45 minutes,
Mhm.
the mathematician 1 hour, and the philosopher 1 hour and a half. So if you want to go to be a philosopher, you can speak how much
So we'll
you
see.
want, but then you are a philosopher. So give attention.
Yes. So we'll see.
No, you can speak.
You can speak
no,
as
I
much as you
understand.
want with the risk that maybe you might be called a philosopher.
Exactly, but
So-
you can speak how much as you want.
So the perceptron controversy was that you cannot rely with one perceptron vector, but a single perceptron is a linear classifier, so really it's not surprising. And I said already in the part 3 of Rosenblatt's book, he calls multi-layer perceptrons MLP. He already said that you need multi-layer perceptrons. But what was missing was a backpropagation algorithm, which was in there were various, I don't know the whole history, but one person would be the Rummel-Williams algorithm, but it was also before. And of course, maybe you have too many weights, so there is something which is called pruning, Principis for and Wolf had also how to prune, to remove the connections in the neural, that would be already a neural networks, which are not so important. Okay, so we see that we have universal realization theorems, but a different kind of what we see in math, because and also you have a universal approximation theorem for continuous functions. But once more, the H here is the Heaviside function, and you can approximate the idea is that you will approximate any function by such rectangle, and each of these is a difference of two Heaviside really. But in practice, it's more difficult. But I just mentioned that since a perceptron in principle is a linear classifier, then it will allow you to give a good approximation to characterize shapes, because each time you have a half plane, and so you can look at shapes like this, for instance. Okay, so now we want classification. So here I mentioned X-ray of COVID pneumonia, and so you'd like to make a classification. So you have two. Let's say you know that you can separate the two classes. How to do this? So this is really the picture we already saw. We already know ahead of time that we have two families which we can separate. It's not always true that we can separate. That will lead us to reproducible spaces and other topics. But if you know that you can separate, can you compute can you hope to get in a bounded number of steps? Can you hope to get the one hyperplane? The hyperplane will not be unique. If it is unique, it will not work here. It's very easy to define a situation where it will be unique. Just put points on the boundary here. But if it's unique, it will not work. So I just recall here what is an hyperplane. It's an equation like this in Rn. So the vector is called a feature vector. If you want, after normalization, think of an apple. You characterize it by a number of characteristics. I mean, its weight, acidity, whatever. You normalize everything. You have a vector. Okay, and this is and so let's say you have two classes. The plus is above the hyperplane is a fancy word to say plane or line when you are in more than 3 dimensions. And so C minus would be when you're below. And so can we compute? I said here V hyperplane is false. I want an hyperplane. V hyperplane certainly not. And so here learning is doing a linear adjustment. We'll see that each time it makes some adjustment. And so here is a recall. So maybe it answers a bit. No, in one moment it will answer a question you have. But here it's just recalling what is the this is really the perceptron, but now how do we do it? So what is the setting? So we have a possibly infinite number of a family of vectors in the feature space Rn. Rn, when you are in machine learning, it doesn't get promoted, it's called feature space. But I mean, it's our usual Rn. And here n is finite, but then you divide it into classes, and you want to find, and we know, I mean, we don't know the A. If we knew the A, there would be nothing to do. But we know there is a A, so that this holds. but we don't know. We want to know that they will be strictly separated, meaning that this infimum is bigger than delta. We don't know the delta, of course, and the bond will be on the bond we have will be depend on the delta. But we suppose that they are strictly separated. So if it is a finite number of elements, this will always be true. I think we take b equals 0. We want an hyperplane which passes through the origin. But if it is infinite, it means really that they do not touch the hyperplane, which we don't know. And under this hypothesis, the hyperplane will not be unique, but this is our hypothesis. But we don't know the A and we don't know the delta, we just know they exist. And from this existence, one can find an algorithm which will separate in a finite number of steps. It's very powerful because they could be infinite for all what we know the classes. So it's a bit strange, but it is true. So what is
for my hyperplane here doesn't mean sub-vector space, right? Because 0 doesn't have to be there.
the hyperplane is a line or
yeah, but they don't have to cross 0, right? They don't have to go through 0.
No. Here it goes through 0, but in general, no.
Okay.
No. If you allow me to backtrack here, you see the hyperplane here, I put a B.
Right, there's a B.
Yeah, but
Fine. Fine.
Fine.
but here I just wanted, I mean, the way it is done, it goes through 0,
Okay.
but you can make a a shift. Okay, so I just repeat myself here that we want a bounded number of steps. And what is the algorithm? It seems well, one has to think about it, but it is iteration. So you start with let's say A0. If it works, fine. Otherwise, you add each time if you're in the wrong side, you add. If you're on the or you add or you remove, depending if you add if your classification was wrong. And this gives you a sequence A0, A1, A2, and the idea is that after a bounded number of steps, it's stationary. Of course, you will never know when it is stationary, so there is a bit of lie here. But because how do I know? I know, but you prove that it will be stationary. But when you do it in practice, you will not know. But still, since you know it will be stationary, when you do it in practice, you can. I mean, this is the theoretical justification, if you want. You know it will be stationary, but there is no. I mean, you ask me how do I know? Well, I cannot. But here is the bond. The bond is 1 over delta squared. So delta was the hypothesis was that we have a which we don't know with this delta. So these are important details for the theorem, but in practice, it's more important to know that we can separate in a bounded. This is what it means. So it has a long history. The proof that I will give, I'm not sure I will give a proof, but the outline is on Nielsen. It's on the book of Minsky and Papert on the perceptron. Now it's interesting that they are precursors. So already in 45, Agmon, before he was a big shot in PDs, he wrote a paper on, not on this, of course, but on kind of linear programming in some sense. And Motzkin and Schoenberg, Howard Schoenberg for the analyst, also worked on this. And but of course, on linear things which are nothing to do with what we, but how to separate linear programming. So I forgot what is linear programming. When I was in engineering school, I studied it, but I mean, I know what it is, but I would not be able to use it. Anyway, the Motzkin was an interesting character, and his thesis was really the beginning of linear programming somehow, but it was in German and it had to be translated before it was recognized as important. Okay, so I will not do the details here, but there are 4 steps. I would like just to mention a bit the steps of the perceptron algorithm. So first, you suppose there is only one class. It seems paradoxical, but it's very easy. You put a -1 of a class, and then they're all in one side. So you suppose there's only one class, and then you normalize. And then you see that every time there is a change, the norm of a square of your the A is the gradient. I mean the orthogonal direction of your plane. The square is m+1. up to here, you don't need the hypothesis. And then here, you suppose that if you have m changes, then you have m plus 1 delta is less than this, and you get a contradiction because here you would have a m squared on the left and the m on the right. So, and the proof, I will not go over it, I think, but it is each time you see, the first one is really by the assumption when you have a wrong direction, something is negative and you put 0 instead. But I will not go into the detail. The other one use Cauchy-Schwarz. So I like also to tell my students that Cauchy-Schwarz is very important. But you see, still the first line here, the second line of each time you add one number, one vector. So it goes a bit upper, a bit lower, a bit at one stage it will be, it will not, you don't add at one stage. You don't need to add. And that's all, but I will not go into the details. I mean, that's,
and this proof works for classes, the classes A and B, or so not being finite.
Yes, no.
Not when discrete, they have to be, right?
No, they don't even have to be discrete, I think. For this, I did triple check, but finite certainly not.
Mm-hmm.
And I think they don't have to be discrete. I don't, as far as I recall. But you get a contradiction like this, is give you a bound on M. So you know that it will be stationary after a certain step, but you don't, of course, in practice, you don't know when this step is. Yes, anyway, so it's, if you want the perceptron is one directional, this is very important, no feedback. I mean, there is no feedback. The feedback would be with backpropagation algorithm. And if you want, it is the smallest artificial neural network which can learn a linear problem. I mean, this is a word to explain what was in the previous slides. And when you need for other more complicated Boolean functions, I don't know why I wrote here nonlinear. Forget about the nonlinear. I mean, for more general Boolean functions, then you need the more, well, what do I want to say here? It's not related really to the algorithm sentence, so maybe we can forget about it. Okay, so now, the mathematical part of the lecture. Suppose we are here, we cannot separate them. So you could think that maybe we can lift, and we can lift a bit, or think we are on like a differential, on a surface, we can kind of pull out the surface and separate them. So the idea is that, this is the input space and you cannot separate them. But maybe you can hope, and in fact, for finite things, it will always be possible when you go in a space which is large enough. You can imagine that if you can map your original data by a one-to-one function in a much higher space, you can hope maybe that you can separate. But what is the problem? Is that what do you gain here? You don't gain anything. If you're in R3 and you go to R1 million, what does it help you? Not very much. So there is a trick to do it. There is a way, I mean, so it's called the kernel trick. I will explain in one moment. But so to go back to my picture here, so if you embed, we could hope that we embed Rm into Rp, where P much larger, with a map T, which would be one-to-one, and that in this larger space we can separate. But what is the problem? T is not good. So the hope was maybe we can use not T, but this function, the inner product of Tx and Ty. And such functions are very important in mathematics. They are called positive definite functions, or approximation kernels. And so we have here a link between machine learning and this very difficult, interesting topic. So now I put here a warning, function analysis Aleph. Now here we need the metric spaces. I will not give all the details. Positive definite matrices, positive definite functions, and approximation kernel invert spaces. But the idea is the following. You have here your points. You are in Rn. Then I have a T of x, which was written as phi of x, but phi of x you are in a much larger Rp. But this is too big. I don't want to, it doesn't help. But instead of this, I want to use this function, which is scalar. Of course, there are no free lunches, and this is a scalar functions of two variables, but still, it helps to make things in a much easier way. So, we will not see the t. The idea is that when we do this, we don't see the t. We will work directly with positive definite functions. These are called positive definite functions when they are such an inner product. We don't see the t. So you don't see that you have a very high dimension, because this here is a scalar dimension. So you go to a much higher dimension via a scalar function, but the scalar function is of two variables, of course. And so this is the idea. But what is behind? So behind is the following thing, which is, I mean, it's a well-known fact, but it's not always explained in books. But it's well-known. I mean, the following. And this is, if you want to know what is I mean, the approach of positive definite kernels, this is really the picture I'm going to do here. Here you have your distance is x minus y, but you don't get. Here is t of x minus t of y. But when you compute the distance t of x minus t of y squared, you get k, and I write k of xy is the inner product of t of x, t of y. You get k of xx plus k of yy, and if it is real, minus 2 k of xy. If it is complex, you need a. So it just means this is a metric. I mean, if it's 1-to-1, so it just says that you have changed. You rather than say you go to a higher dimension, you can say I'm saying on the same set, but I change the metric, and in this new metric I can separate. And but you see, when I'm here, I don't see the t. I don't care about it. Here it's just in terms of a kernel. Of course, one link is missing. I will explain in one moment. The link which is missing is what are these functions which we want? And these functions are exactly the functions which we can factorize. Maybe that it will be infinite dimensional, but k of xy, we will call it positive definite if and only if we can factorize. I have to give some definitions, but I don't want to give too many definitions. But this is the key. If you want, really the key. And in most machine learning books, it's not written, although it's a fact which is known for a very long time, is that this is, when you take a square root, if you want less here, this is a new metric on your space. So you say on the same space, but you have a new metric on it, that's all. And so with a new metric, you can know that you can separate. Sometimes yes, sometimes no. So this is the difference of the definition of a metric space, a metric. Just for fun, I just wanted to mention this fact. It's not related, it's kind of intermezzo, yes. So you see, let's say you want to, so it's not related to what I said before and to what I will say after, but I think it's an interesting fact. So I look at sets. So A, B, finite sets. You see what's written upstairs, D of AB, the cardinal of the symmetric difference divided by the cardinal of a union, it's a distance. It's not so easy to prove, but it is a distance. But sometimes you don't want the distance, you want to see when things are similar. And then you look here at 1 minus D, the cardinal of the intersection divided by the cardinal of a union. Then it's a measure of similarity. And this was found already in 1901 by Swiss botanist Jacquard, who he called it coefficient communauté. He wanted to compare floras in different parts of Switzerland. And you see, think about if you want think about a supermarket and you have two shopping carts. So you want to compare, you would compare what is together and the union. You will not compare with the whole thing. And this is what's called well, it's a similarity. It's not they call it similarity metric, but it's not a metric. But just a small interruption. I think it was what is interesting is that Jacquard did this in 1901. I mean, before geometric spaces and everything, he did this for his own purposes, and then it was rediscovered. So in any event, so in one line we just change the metric. This is what I already said a couple of times. And you see an example here. So this is a positive metric. You have the original feature, and you add when you put powers. Also, you add dimensions. But one thing is missing here. So, and downstairs I see how I can factorize. One thing is missing is what is the connection between positive definite, between how can we characterize these functions? Is there a way to characterize these functions independent of a t? So there would be two different facts. First, I characterize them in a way independent of a t, but I know there is a t, so I know it corresponds to what we want to do. And these are called positive definite functions. The definition is here. I will go quickly about this. I mean, for those of you who are interested, I have my slides where I can give more details. I don't think it is a very important notion, but I will not give too much details. The important fact is that there is a whole theory of positive definite functions, and we can use this whole theory to. I mean, I don't do this, but one can use to do this separation with what in machine learning they call the kernel trick. But is used. So this is and there is, so forget about this one. The key here is a factorization property that the function is positive definite, and this we know to work if and only if it is factorizable. So here you have a map. This is also the map, but this is a map in some sense which is connected to the machine learning. What is important is that sum and products of positive definite functions are still positive definite, and so you can play a lot and find new ways to connect. There are a lot of very interesting mathematics behind this. What I'm going to say here is a bit different. The last slides are a bit different. If you're up to the previous slide, it is related to the perceptron really. We explain the perceptron, and when we cannot separate, we go to a higher dimension. So this is, in some sense, almost the end of the talk. What I wanted to mention here is something a bit different, but quite often, in fact, in machine learning, these are interpolation problems, I already mentioned, but a different type. Because you don't use Hermite polynomials or whatever. These are functions of a completely different type, which you get by iteration and so on. So these are different kind of problems which, when a mathematician looks at this, it seems very strange. So it can be function of this type and the composition of them. So it's very strange. You get strange problems. Some mathematicians have tried to work on this. I don't think there are very much results, but some mathematicians have tried to. I know a couple of papers, but it's not so easy. We're speaking about Heaviside functions, so one can do some other functions. You see, the Heaviside function is not continuous. Now, this function here, the sigmoid function, not only it is differentiable, but you have here this relation. So when you look for formulas and you have a connection between the derivative and the function, it makes formulas much easier, in particular for the backpropagation algorithm. And here is another one with a hyperbolic tangent and another connection. The importance here is that it looks like the Heaviside function, but there is an underlying ODE, I mean phi prime here, which in fact allows you to get nice formula in some sense. And here I will really finish, but we saw, so if you want, there is a whole part of, which I've not discussed, and the point of the lecture was perceptron, but there is a whole part which is very interesting about the collective emergent properties when you have large, and and this really brings us to Hopfield networks really, where I will not discuss them, but it will be another talk. But he uses the metropolis algorithm I mentioned at the beginning. He has a notion of energy and memories. It's content addressable memories, not random, are really like minimum energy things. So this is a thing which are completely different. So this is a report. The Hopfield model. I mean, optimally there would be McCullogh, Pitts, Rosenblatt, and Hopfield. But I mean, Hopfield would take us too long. But he introduced. Well, it's very difficult to say introduce. I guess it was also before, but the notion of energy. And so he wanted to minimize the energy, and minimum energy corresponding to stable states, which are like your memories. So that's the idea, and it's explained also in the book of Daniel Hamid. So I would like to conclude here. So I just want to mention that there are a number of very important differences between artificial neural networks and classical computers, which we can see from what I discussed a bit before, delocalization, that there will be content addressable memories rather than random access memories, and emergent properties. But I didn't discuss this, but still, and I would like to say that machine learning uses a lot of mathematical tools. This is why I like to teach. What I teach at CAS is the mathematics behind it, not the algorithm. And I mentioned here something like graph theory, dynamical system, metric spaces. You see here a paper, a book using algebraic geometry, and I would like to say that you pick your favorite math field. It has been used or will be used, really. So this is what I wanted to say. The last part I was a bit quick, but I mean it would be to go to the. I would encourage you to go to the papers of Hopfield and see. And these are really the main ideas behind Hopfield. So that's I will stop here. Thank you.